Equation 10 is the same thing as equation 11. And in case you forgot, this equation 11 is exactly the same equation that we got earlier when we developed the so-called informal fast Fourier transform. This represents the so-called inner product operation. Okay? In fact, here it is. Equation 11 that we just obtained now play exactly the same role like equation 10 earlier when we talk about the informal development of the fast Fourier transform. So far, let's see what did we have. We already compute the inner product to obtain the vector f1. So what is the next thing we can do? I hope you still remember. Let's see now. What is the next thing? After we obtain the vector f1, what is the next thing that we can do? Right here. You see? Right now, we just obtained the vector f1. After that, what we should do is we take this term, which is w raised to the power 2n1 plus n0, the whole thing times k0, as shown in equation 7. Multiply that with the inner product vector f1 that you just computed, and the product of this f1 and that term w over there together, we call it the vector f2. Okay? And that vector f2 should be the same as the vector c theta. So let's see what is the next thing we do. So after we calculate the vector f1 based on equation 10 or equation 11, the same thing. Now we say, just like I told you, the vector f2 is equal to the w raised to that power term, and then you multiply that with the vector f1 that you just calculated. And now you have to do the summation on the index k0. Why? Why you do the summation on the index k0? The reason is because if you go back to that equation right there, you see, for the inner product, you already finished it. Now you have to do the summation on the index k0, as I show you right there in equation 7. Okay, so let's see. So let's do the vector f2 is equal to the w raised to the power term times the vector f1 that you just calculated. This time you do the summation on the index k0. Now, let's see what happened. The first thing, just like before, you let k0 equal to 0. So let's see what happened. You let k0 equal to 0. You see right there? And then you let k0 equal to 0. That way, you can get this term of equation 12. Then, after that, you let k0 equal to 1. When you let k0 equal to 1, this is what you have. And also, you let k0 equal to 1, this is what you have. So, this term here, what you got is another term of equation 12. And you have to add them up together. So that will give you the value of f2 and 0, comma, and 1. And again, you can simplify a little bit more. The reason you can simplify is because 0 times anything is still 0. And then when you take w raised to the power 0, the whole thing becomes 1. And that's why the previous equation now can be simplified to become equation 13. You see? So what you have left, if you can see f1 and 0, comma 0, that term is right here. and then the next term you have is the blue term, and that term is right there. So this is what we have, equation 13, to compute f2 of n0, comma n1. That's what you have. The next thing we can say is this. If you take a look one more time at equation 13, that equation 13 actually contains 4 equations. And the reason you have 4 equations is because you may have a different combination value for n0 and n1. For example, when you let n0 and n1 equal to 0, comma 0, then you should get equation right hand side, the right hand side equation 13. When you let n0 equal to 0 and n1 equal to 0. You see, let n0 equal to 0 and you let n1 also equal to 0. Similarly, if you let n0 equal to 0, n1 equal to 1, then you get another equation. And then if you let n0 equal to 1, n1 equal to 0, you get a third equation. And then finally, you get n0, let's say, equal to 1, and n1 equal to 1, then you get the fourth equation. So what I'm trying to tell you is equation 13 actually can give you 4 equations depending on the combination of the value n0, n1 that you want to have. So that is exactly right here. See? So when you let n0 and n1 equal to 0, comma 0, then you get the first equation. When you let n0 and n1 equal to 0 and 1, you get the second equation. When you let n0 equal to 1, n1 equal to 0, then you get the third equation. And when you let n0 and n1 both equal to 1 and 1, then you get the fourth equation. So these 4 equations, you got it, based on the previous formula, can again be represented in the matrix notation. So for example, the vector f2 that you computed from equation 14 is represented right here on the left hand side of equation 15. And then similarly, the right hand side of the 4 equations that I show you there in equation 14 can be expressed as a matrix 4 by 4 times a vector f1, which is 4 by 1. Again, if you look at equation 15, that is exactly the same equation I developed for you a couple of lectures ago when we talk about informal development of the fast Fourier transform. Same, play the same role. Okay, that's what I said in this slide. Equation 15 that we just obtained play the same role as equation 12 that we developed earlier in the informal fast Fourier transform. Now you have to be careful because your original objective, you're supposed to want to calculate the unknown vector c theta of n1, comma n0. However, at the end, after you calculate the vector f2, what you got is the vector f2 of n0, comma n1. In other words, what you compute for f2, it is not in the same order like what you would like to receive. And therefore, after you obtain for f2, you have to go through the so-called reverse ordering, which we call like the unscrambling process. Unscrambling process that we talked to you earlier when we talk about the informal fast Fourier transform. You see, because the order here is n1, comma n0, this is n0, comma n1. So after you get f2, you have to reverse the order of the bit in here in order to get into the right way. All right. So that is the story. And that is the end of this lecture. Here's the acknowledgement.